Hello. So in this unit, the applied problems that we're going to do, there are two kinds of applied problems, which will turn out to have equations as rational equations that we've been working on already in the rest of the unit. So the first one is called distance problems. Okay, distance problems. It means we use the formula rate times time equals distance. Please write it like this. I don't like it the other way, d equals rt, because we don't ever do anything like that. We don't say 15 equals 3 times 5. We say 3 times 5 equals 15. Not only that, if you use RTD, you think RTD, well, what else do we have around here that's RTD? So yeah, our bus. So it just can help you remember. Rate times time equals distance. So when we are talking about distance problems, we're talking about cars driving or people running or walking or bikes going or boats going up and down the river or planes flying, all those kinds of things. Okay, so one thing that is really important to always keep in mind. So we're going to do a chart, and I'll show you how to do that. And on the part where we do rate, whenever we're doing rate for distance problems, the thing comes first. So if we're talking about boats, let's say, so B would equal boat, the speed of the boat. C would equal the speed of the current. P would equal the speed of the plane. And W is equal the speed of the wind, etc. Things like that, okay? So when we do this, the speed of the boat or the speed of the plane must always come first. Then we will add or subtract. If it's the boat, the speed of the current. If it's the plane, the speed of the wind. Okay, and that is our actual speed, our rate. Okay, you need to think, if you did it the other way around and you put in, say, the speed of the wind plus or minus the speed of the plane, basically what you are saying then is the plane is affecting how fast the wind is blowing. Is that possible? Or you are saying, if you put current first and boat second, you are saying that the boat is determining how fast the current is flowing. Is that possible? Well, it's not. So always do the speed of the boat or the plane first, and then the speed of the current or the wind second. Now, when the boat is going with the current or the plane is going with the wind, it's going to go faster. So we add the current or the wind. When the boat goes against the current, then, or the plane goes against the wind, then it's going to go slower. So we subtract it. Also, going against for a boat means going upstream, and with means going downstream for a boat. Okay? So what that means is, depending on our kind of problem, sometimes our X will be the boat, or it might be the plane, and sometimes our X will be the current, or it will be the wind. So we don't know. Sometimes we do X minus a number or X plus a number. Sometimes we do a number plus or minus an X. Okay? Let's actually just get into doing some problems here. So here's our first one. And always read the problem first. And remember, this is called an applied problem now. We don't call them word problems anymore. With a current flowing at 4 miles per hour, a boat can travel 32 miles with the current, that means going downstream. In the same amount of time, it can go 24 miles against the current, going upstream. Find the speed of the boat in still water. Now, I only need to know that the speed of the boat in still water is because technically the current is going to affect how fast the speed of the boat is going. So I don't really need that, but they have to put it in there because it's specific to math. So I don't need that in the final answer, the still water, because there really is no such thing as still water. Think about any river you've ever seen, any ocean, even any lake. It's always moving. Same with wind. Have you ever known there to be absolutely no wind, even a teeny tiny bit? Okay. But they have to put that in there with the idea that this is the speed and then the wind or the current is affecting it. All right. So, in the same amount of time is also very important thing for me to know. Sorry about that. So, meaning that, let's say it takes me 2 hours to go upstream and that took me 24 miles, then I'm going to go for 2 hours downstream and I end up going 32 miles, but I still only traveled 2 hours each way. The time is exactly the same. Time equals time for this problem. Okay? So now we're going to set up our chart. What do we call this? I'll come up with a word in a minute. Anyway, so we've got, table. It's a table. Rate times time equals distance. And this is a boat, so we've got upstream, which is against the current, and downstream, which is with the current. So I know, forgive me, before we do this, it's very important that we set up or we assign our variables. If you do not assign your variables, it's going to be very, very difficult to do these problems. And assigning a variable is always say, let X, or whatever letter you want it to be, equal. Okay? And now we describe in words what X is going to be without numbers, except in very specific cases, but I don't think we have any of those in this unit. So in this case, let X equal the speed of the boat. Now we need to be very specific. If you just said let X equal the boat, that's not specific enough. Think about this. If I said let X equal coins, that is very non-specific. It's not going to help us in any way, shape, or form. But what if I said, let D equal the number of dimes in the purse? That is very specific, and that will help us. So this thing here, after you do let X, should be a description of what X is in words, being very specific. Okay, so now we're going to set up our table. So we've got rate, time, distance. We've got upstream, again, which is against the current, and downstream, which is with the current. So I know that my X is the speed of the boat. So that has to come first. That's the boat. And then upstream is minus and downstream is plus. Well, let's go back and see. Oh, the current is flowing at 4 miles. So the current is what comes second. Remember? Boat minus current, boat plus current. Okay? Then I look at this and it says a boat can travel 32 miles with. Well, that means going downstream. And 32 miles is distance. Miles is distance. Miles per hour is speed or rate. Okay? And then it also says it can go 24 miles against the current. Well, against means upstream, and so that's 24. Now, I don't have T. How can I, and there's nothing in here except that it says it's the same amount of time. So I have nothing that tells me what t is. But think about this. If I have r times t equals d, and I wanted to solve for t, how do I get t by itself? Well, to get t by itself, I need to divide by r. If I divide by r on one side, I need to do it on the other. And that leaves me with t equals d over r. Well, do I have a d? I do. Do I have an r? I do. So d over r, d over r, these are my times. And remember it said in the same amount of time. Time equals time. Well, now I've got time and I've got time. And that is our equation. 24x minus 4 equals 32x plus 4. Time equals time. Now, you could work this as you've been doing by finding an LCM and doing all that, or you can do this because it's one fraction equaling one fraction. Even if I had a plus 1 over here, I couldn't do what I'm going to show you now. But if it's one fraction equaling one fraction, I can do what's called cross multiplying. And so I can multiply 24 times x plus 4, and that would equal, and I can multiply 32 times x minus 4. Now it's 24x plus, well, let's see, 24 times 4 is 96, and 32x, 32 times 4 is 128 minus 128. Well, this guy's bigger, so I want to move this guy over to the other side, which means this guy has to go to the other side as well. So I'm going to subtract the 24 here, add the 128 there. So 32 minus 24 is 8x, and 128 plus 96 is 224. Now I just need to divide by 8, and 8 goes into 224. That's twice, that's 16, that's 64, so that's 8. X equals 8. And x is, the speed of my boat, and this is an applied problem, so my final answer has to be in a complete sentence. So the speed of the boat is 28 miles per hour. And there you go. I'm going to do another one in the next video.